Does it work? All right. Hello, everyone. My name is Ole André Valranos, and I work as a security researcher at NowSecure, and also the creator of Frida, which I'm going to show you a bit of today. Because what I'm going to talk about is something that's new in Frida, probably the coolest new thing in Frida since Frida was created, and I think we should really integrate this in R2 Frida and do awesome things with it. I'm not sure what people will do with it yet, so that's why I'm going to just show some demos and get some ideas flowing through your heads, and maybe there will be contributions in the future, or that's my hope anyway. That's the goal of doing this. But before I do this, some of you are probably not familiar with the Frida API, so I'll just spend a few minutes on a quick introduction. Oh yeah, thank you. So essentially what Frida is that you have this process debuggy on the right here, where you want to run some code inside of that process, and you are the debugger on the outside. And so what Frida does is it allocates some memory for a so-called bootstrapper inside there, some code, and then it creates a thread that runs that code, and that code then just loads a library from the file system, or maps into memory, depends on the OS, and then that establishes a communication channel back to you. And finally, that allows you to tell it over the communication channel, please execute this JavaScript, and this has a JavaScript interpreter inside, and that allows you to access a lot of APIs to introspect and augment functionality and do many fun things. So let's just dive straight into the code. So we're gonna, for the sake of keeping things simple, we're just gonna start by writing a tiny program. Oops, I'm still not used to this keyboard. Bear with me. We'll have our main function. And we're gonna have an infinite loop. And every second we're going to call a function, and we're going to give it an integer n that's increasing every time. And we're just going to sleep a second between each call. And we need UniSTD for sleep. And yeah, that's it. And of course we need to write this function. And has an integer n. And it's just going to printf number on standard out. All right. I probably made a typo here. Oops, what am I doing? Okay. And yeah, one more thing. We should probably also print out where f is in memory, the function f that we're calling. Okay, we're ready. So if we launch this, it's calling the function every time, and it's printing out the integer that is given. Okay, now we're just gonna have some fun with Frida using the Python bindings. So just import Frida, and we're gonna attach to the hello process. We could also attach to it by PID, and then we're gonna tell it to load some JavaScript. And initially, yeah, maybe what we want to do is just, actually, yeah, we're gonna use, actually to make this easier to read, I'm just gonna open it from a file. So, so the code we want is here, and we're gonna load the script, and we don't want this process to exit immediately. We want to keep it alive, so we're just gonna lock in standard in. Yeah. And then we're gonna write this code that we want to inject. So we start a new file, explore.js here. And we know we have a function at this address here. So we're gonna now hook it, create an inline hook, so we get a callback. And keep in mind that this JavaScript is going to be loaded inside the other process, so we have full access to memory, and it's called synchronously, so we can even change things, but I'll get to that. So we use an API called interceptor. We tell it to attach. We give it a pointer to the function. It can be any function in memory. It doesn't have to be exported. All it needs to know is the address. It doesn't even need to know the ABI or number of arguments or anything. And we're going to define an onEnter. And this gives us access to the arguments. So we can just f was called, and then we could print out the first argument as an int 32. And now, if I now run this, and hopefully, yeah. So you see, we're logging f was called and the number. So we're taking the argument and we're printing it out. Okay. So what I did now is, yeah, we figure out what the argument is. But anyway, it's that we have to write this Python. This Python code is probably a bit. It makes sense if you're writing a tool, but maybe it's overkill for this example. So we could use the REPL that Frida has. So you run Frida and the name of the process and the script to load. And here it is. It's running. And the cool thing now is that we can actually go in here and change the code. F was called and save, and it's instantly updated. So you can actually change things live, and when these scripts get unloaded, they will revert all the hooks in memory, and then when it loads again, it's going to apply new ones. So that's how you can dynamically explore, observe things and then realize you need to add more logging in a certain way and so on. But this is what's really easy now with r2 Frida, but I'm just showing you how you would do it from the bare metal. Yeah, library loads. Another thing you might want to do is we could change the argument. So args0 is assign a pointer, and we could assign how about 1337, and if I do that, you see that it changes on the right now, because now the function observes a new argument. And you could also, yeah, of course, take the original argument and add 9,000 to it. Oops, can't type. Yeah, pointer. And there we go. Now the numbers are incremented by 9,000, and we can remove it, and it's back to normal. Because actually, we're just modifying it when it's calling the function. We're not modifying the original value on the stack of the caller function. That's why it's back to normal when I revert now. And another thing is you can also replace functions. So in this case, we already know this program that we're playing around with. So we know that it's calling sleep. So we could then go ahead and interceptor replace instead. And we need to find the address of the sleep function. So we do module find expert by name sleep, and we need to now replace it with something. So we can do a new native callback that will allow us to get a callback from native code. We just need to declare the signature. And now looking at the documentation of sleep. Oops, wrong one. It returns a uint and accepts a uint. Okay, fine. So we specify the argument, the return type, and then an array of argument types. And here, instead of actually, we could call the original sleep, but we could also use Frida's API to just sleep, say 50 milliseconds, whatever it's given, it's going to sleep 50 milliseconds instead. And if you pay attention on the right now, when I save this, Oops, there's a typo. Yeah. Interceptor. Okay, and now it's speeding up. So now we are replacing sleep with our own implementation. And we can save it again, and it's back to normal. And another thing you might want to do is, this is typically for fuzzing or interacting with internal APIs, is that you can also call functions. So we could do a new native function, and we know the address of the function because we printed out in the beginning here, but we could also use Frida's APIs to resolve this other ways. And we're going to say its return type is void and has one int as an argument, or actually, yeah, an int. And we can now just call it, oops, say 5 times. And if I scroll up to the bottom here and I run this now, yeah, you see 5 calls happen here. So this way you can, yeah, you can call into APIs that's available to this process. And yeah, there's ways you can communicate with these scripts, but I'm not going to cover that because that documentation covers it well already. But one thing I should probably mention is that you can also interact with Objective-C and Java APIs, as Francesco said yesterday. So I'm just going to show you. So let me think. Yeah, let's use a more interesting application like Twitter. And we can use the REPL just, and you have like Object-C classes stuff and so on to access the classes in memory. Now another thing we could do is, like, for example, we could see what kind of files this application is opening by attaching to the open function. Arguments and print out open, and we can now use another API to treat the first argument. It's a pointer, but we treat it as we can read it out as a string. Oops, yeah. And now if I interact with it, you'll see that it's calling open a bunch of times here. And now I was going to show you actually that we can also call Objective-C APIs. So there's like Objective-C classes. How about there's an NS speech synthesizer API, okay. Sounds fun. Okay, and we're interacting with Objective-C code, so we should have an NS auto release pool. Actually, we can simplify that. We can just do no. Yeah, we can do that. Sorry. Oh no, I changed my mind. Yeah, we'll do this. So we're gonna take the NS auto release pool, alloc it in it, and then we're gonna release it. And between here, we can actually call APIs. You wouldn't have to do this if you did Object-C schedule on the main queue to schedule some code on the main thread. But here we just need to set up an object once, and we can use it. So we want to create our synthesizer. And we look at the docs to find out the API. And we probably want to... Actually, I'm going to cheat a bit now and look at my notes. So so we don't spend too much time on this. Was it here? No, here. Yeah. So we allocate an init standard, and then we're gonna get a voice ID we want to use. So we're just gonna call NS speech synthesizer available voices object at index 2, for example. Well, 0 is probably more safe. I don't know what's at 2. And then we're gonna tell the synth to set voice ID. And then here, when open is called to open a file, we can now ask the synthesizer to start speaking something. So synth start speaking string. Oh, yeah, and it may be just the name of the file. So extract that in a variable here. Okay. Twitter is still running. Yep. Okay. Save this.
/BR /folders /QB /user /BR /folders /QB /X1B44679141 G7XHTMVSC 5WinM00000GN /2/com.twitter.twitter-map /tempo all the items /a document being saved by Twitter.
That's enough. Okay, so that's the Frida basics. Onto the talk. Yeah, I'm going to talk about an API that has been in Frida for a long time. It's called Stalker. It's all about code tracing. So what we did just before now is that we did inline hooking. That means that the original functions are modified. You can also modify in the middle of functions by a slightly different syntax, but essentially you're modifying the code in memory, and any thread that's calling that code get trapped or go into JavaScript or do what we want. But sometimes you might not want to do that. Actually, if you don't know what kind of APIs are being used or what code is being used, that's a use case for Stalker, which has some other nice properties like not actually touching the code in memory, so it's more stealthy in that sense. There's how this started was that I was reverse engineering Apple stuff, and they had a nasty obfuscation scheme, and I wanted the code tracer, and the existing ones were slow, so I wanted to avoid this whole context switch dance between the debugger and the debuggee. I just wanted to do it tracing in process, like Pin and Dynamo, but actually scriptable from JavaScript. And there should be identical side effects, so that the program wouldn't be able to tell that it's not actually the original code that's running, because it would take the next instructions that are about to run. I'm going to explain this more in detail later, but take the next instructions and recompile them dynamically to add the instrumentation between them, and but making sure that they have the same side effects. So if you're calling if there's a call, it will actually push the same address on the stack on x86 as if the original code had been running, even if the code running is somewhere else in memory. And of course, this should be high granularity, so you can actually combine this with the inline hooking that you saw earlier. So where you could, whenever a function is called, a certain function that you know about is called, you could start tracing from that point on until it's leaving that function. That way you can take an interesting private API on an Apple platform, for example, and just start stalking from that point, and you will know all the APIs it's using under the hood through whichever libraries it's using. And yeah, let's just try to use this API. I guess we should use a calculator for this. I don't know why, but let's use that. It's a simple program. And we're going to write some slightly different code now. Quite different. Yeah, we're going to ask the process API in Frida to enumerate all the threads. Okay, all the threads. And each thread, we're going to run some code. Okay. And then we're going to do stalker follow this thread ID. And then you have to tell it what kind of events you're interested in. So you could say that you're interested in all the call instructions, for example. And then you have two options. You could get a periodic a dump of all the calls that happen, all the function calls. But that's a lot of data, but you'll get them in sequence. So, and you also have the depth of the calls and so on. And you have another way, which is like a summary, which just tells you the targets and the number of times each was called. We could start with the one that's very verbose. So you implement on receive, and you get some raw events here. And then this is just raw data, so binary data. So you could save it for offline parsing later, or we could parse it right away, like this. So we parse them, and now we can do it for each event. Maybe this is actually a dumb thing to do. It's better to just console log the whole thing. It's going to be hard to read anyway, but at least this will be faster. So we're going to enumerate all the threads, follow each of them, and say that we're interested in call instructions, and then every time we get a batch, we just display it. Okay. And now we want to load into calculator this script here. Okay, and now if I interact, yeah, there we go. The first batch. So you'll see you get the type of the event, call. You have where the call is in memory and the target of the call and the depth of the stack. So you could then visualize this, and there's a lot of data though, but yeah, you can actually use the application while it's tracing it. There is one thing to note though, that this produces a lot of data. So you have on the stalker you have a queue size thing. I forgot actually what it's called. But here's the API reference. Queue capacity, and that defaults to 16,384 events. So you can bump that if you need, if you want to use more memory. And you can just look if the events you got here, if you got 16,384, it means here it's probably overflowed, and you should set a higher limit. And you can also control how often these events are drained and given to you. But by default, it's 4 times per second. Okay, so that's more or less the basic Stalker API. You have other events, so you can notify the call instructions, write instructions, exec for every single instruction. You have block, which is basic block level, and you have compile, which is only the first time something is compiled, so you can use that for coverage. Yeah, you have one more feature, and that's something called call probes. So you can say for a given call target, get a synchronous callback, so you can look at the arguments and things like that. And I'm just going to show you a proof of concept application built on top of a traditional Stalker API. So we haven't gotten to the new stuff yet. I want to walk through the history of what you could do previously. So here I built proof of concept Qt GUI that you could select a process. Frida gives you a process list that has icons even, and then you get the threads that we just used that API, so it's the same thing as using. And it's also using interceptor attached that we used to hook functions earlier, to hook a few strategic APIs. And then it tags these threads here with based on what kind of APIs they're calling. So you could get an idea that this thread is probably a file and networking IPC thread and so on. And then it allows you to then pick a thread and follow, which uses a stalker. And then you'll have the call. Actually, here it's using the call summary to get all the summary of the call destinations and the number of calls. And then you can browse around. So that was the idea. And then you could add the call probe, which is the feature I talked about in the end. And that is what you see there in the dump there. And then you could click on any of those and change the code live. So you could have could look at the arguments and yeah. So this was like a reversing tool, or the idea was to show that you could build that kind of tools. It hasn't evolved since then. It was just more like a way to show what's possible. I think we should do this. I mean, we should build this kind of cool stuff in R2 Frida and not have 100 tools that don't work. But it's just showing that it's easy to make new tools. Some weeks before r2con, I was working on a bug on Android, and I had a problem where there was the art runtime on Android has some internal APIs that are not exposed, or they're actually part of, they're inlined in the code all over the place. It's C++ classes, template classes. But there was one particular place in the code where there was just one assignment and nothing else happening. So I could just, in theory, take this function and copy the whole contents, but I skip the instruction in the middle. So I was thinking this would be nice to use Frida's existing APIs for this, because it already has API to generate code and transform code, so you can take some code from one location in memory and dynamically translate it so it will work in another location in memory, copy it, relocate it, so position-dependent instructions are adjusted. So I'm just going to show that quickly. So I've exposed these APIs to JavaScript. Yeah, I should probably stop this thing first. And it looks a bit like this. So we could have a page of memory. And we could have a code writer. So there's x86 writer if you're in x86. There's ARM64 writer if you're in an ARM64 process, and so on. And now we can say we could put a move reg u32. We want to move to XAX. That means EAX on 32-bit, RAX on 64-bit. So it allows you to write somewhat portable assembly code for x86. The number 42. I screwed something up here. Yeah. Invalid argument. Oh yeah, thanks. Dope. Yeah, of course. It would have worked if we used EAX but yeah, we could just update the whole register. Okay, we should probably reset the code writer back to the beginning. Okay, we put a move EAX RAX 42, and then we could put a ret, and then we can flush. It's not very necessary in this case. And now we can actually create we can actually call this function. Well, we have the memory protected first. The page size RWX, okay, and then the page, it returns an int and no arguments. We can call it 42. So that's how you can generate code. There's also an API then, x86 relocator, to relocate code from one location to another. But yeah, the natural step then was like, yeah, Stalker can do code tracing, but what if you could influence the code that it's generating? because now we have the building blocks to do that. As you could see, you can generate code. I'm just going to show that. I'm going to go back to the calculator. And yeah, we can actually use the same boilerplate, but instead of, so we just start or follow, and the new thing here is transform. So you can give it a function, and this function will get called on every single basic block, and the default implementation will just do while iterator next, not null, iterator keep. So that just tells it, okay, this instruction I want to keep it. If you don't call keep, it's going to skip the instruction, so you can actually replace instructions with your own instructions. And another cool thing here is that you get the instruction when you call next, and then you can look at it and you can put some code before the original instruction or after, depending on where you, if you add the code before you call keep or after. But I'm going to show that. So we can just start with this default implementation, but maybe we can actually show you the instruction. So we're just going to assign it to a variable. Okay. And have the calculator running. Yeah, okay. And there we go. Lots of code is being recompiled as it's running. And if I now interact with the calculator, it should be a lot more. So this is the compilation process is happening now. I'm slowing it down a lot because I have this console log in the path of it. But what's cool about this is that you could do like, say you're only interested in call instructions that happen inside the application itself, then you could do like a new module map, and you can filter that. Module. So that if the library where this basic block is has calculator.app in this path, then we want to include it in this module map here. And that allows us here in this code to say if not app has this instruction's address. Actually, we need to get the instruction for the first instruction, so we just iterator next here. So if it doesn't have it, well, we just want to have like the default implementation. We keep all the instructions and we do nothing else, and then we just return. So we have like a default implementation for non-app code, so we don't have to trace or instrument or care about that code. And we also need to change this into a do while. So we keep all instructions. Now there should be a lot less data. It's probably still going to be too much, but we'll see. Oh, not too bad, actually. Yeah, so the calculator doesn't have a ton of code of its own, so this makes it, limits the search space. Because now we can actually add some more things here, like, okay, we got an instruction. If this instruction's mnemonic is ret, it's a ret instruction. Maybe we actually want to look at the return value. Hypothetically, like it might have something in REX. And what is now with this iterator, you can put move reg blah blah blah. You can add your own code, anywhere, but you can also put a call out to JavaScript. So on ret, so just iterator put call out on ret, and I'm defining an on ret here. And I'm logging ret at context PC. So now anytime there's a ret instruction, we put a call back into JavaScript, and this put call out here will actually make sure to save flags and registers and avoid the red zone and so on. So it takes care of all the details, so you can safely call into JavaScript. So we can just restart with this and see what happens. Yeah. So you see a bunch of calls now for each call instruction inside this app. And then you could go ahead and do more fun things like just to save time, I'm gonna just copy some code I wrote. Yeah, there we go. Oh no, not that one. What you could imagine doing then is you could save just the flags, and then you could save a register, and then let's see here. Actually, I'm just gonna reuse this code so you don't have to watch me type it. So what you can do is, well, we know that we're at the ret instruction, so it's probably safe to modify flags. We're just going to assume that. We could save the flags and restore them, but so we're just going to compare EAX to 60, and if it's below, we go to nope here. And if it's above 90, we also go to nope. So if it's between 60 and 90, we actually put we call into JavaScript here. And REX is this value. And one thing to be careful about is that you put code on the right side of the keep here, because if you put code after a ret instruction, it doesn't make sense and it won't be reached. So in this case, it's a ret instruction, we put it before, that's why we have the code before calling keep here. Yeah. So we don't see anything. Okay, let's adjust. Say 3 and 10. Yeah, there was some 5s. And yeah, now we can bring back the speech synthesizer and make it call out the return values if we want to. Yeah, let's just do it. Oh yeah, just forgot a few things here. The imports.
Five.
Yep, it works. So you can combine many things in interesting ways. And I think I'm running low on time, so I'm just gonna now go to how the things work. So the way Stalker works is that you have the original code on the left. It's at 0x1000 here, 1000, and we take this code and we recompile it into this. So we keep this move AX just as it is, and then we have a prologue where we save stuff, and then we have an epilogue after. But between here, we actually ask the Stalker to compile the target of the jump here. So it's 1, 2, 3, 4. So because we stop on the first branch instruction. So that will set a resume at variable, and it's going to jump to that afterwards. That's like more or less how it works. And then this gets then we have another block, and well, it's similar, same thing. But this is really slow because you're saving a lot of registers here in the prologue and epilogue, having to go in and look up if you already compiled this block and so on. So Stalker has some just-in-time tricks where it actually, if you look at the first block here, it's calling the second block, jumping to the second block, and it can then back patch and just write a jump directly to the beginning of this one, the generated code for this one. But this assumes that the code isn't self-modifying, so you have a way to control that. So you can tell it to not trust code to change. So it will always go and check if the code changed, and only then reuse the code. Or if you tell it to trust the code a bit more, then it will do it after an execution, sort of lock without change. And that means that with this trick and some inline caching tricks, we run between 1 and 2x slowdown compared to the original code. So it can run really fast and only add a few % overhead. Depends how much callouts you add or how much instrumentation you want. But that was only recently that this became really much faster. On x86 it was about 4 times slower because it only implemented the static back patching trick. But now it also has the dynamic inline caches that does, like, if it's a register, it will, or a register memory location target, then it's going to have some inline compares where it's going to fill out those values as it's running. And now it's that made it 4 times faster. On ARM64, where it's also available, it was 22 times slower, and now and then after the static backpatching trick, it was 2.2 times slower, and after the dynamic tricks, it's now also 1 to 2x, so it can run code really fast. So you could, I'm going to show this now. We could have a more complicated example, like some app, some game. Did it actually load? Oh, okay, it's loading. Okay, so Frida, the name of this process, something with road trip 2. Can load this Explore.js. It's going to be a bit slow in the beginning, but it should catch up. Or it's going to crash, we'll see. Actually, maybe the speech synthesizer is a bad idea. Let's just remove this code here for now. So for the rest instruction we print it, that should be okay. Okay, it's not dead yet. So the thing is, it will be slow in the beginning when it's compiling all the code, and it's going to speed up. But This part of the demo is not very well prepared. So it was last night, very late. So. Let's just try to... get it working. No, calculator app. Wait a minute. Okay. Yep, it's still alive. That doesn't like me switching. Yeah, we're tracing all the threads and they're still running. Anyway. Any questions? Hey.
What injection methods do you use in Windows, for example? Can I use it for applications that refuse to be injected?
There's several ways. So the injection method is RTL create user thread or something. I forgot. You can also use it. There's another thing in Frida called gadget. So you can somehow make the app load that library DLL, and after that you can communicate with that. So
From kernel land?
that's not explored yet. So you have to. Yeah, there will be some work to get into the kernel, I think.
Okay, thank
Hey.
Yeah, I'm trying to understand how it works. So it was a bit. Hi, can you hear me? Yeah.
Yep.
So yeah, it was very interesting. I'm just trying to understand how it works. So I understand that you recompile to your own code and that it gets injected somewhere in the binary. But then how do you redirect from the, let's say, the old code to the patch code?
Yeah, you mean you're talking about interceptor that I showed earlier with like the open
I guess anything, any prop that you make or the stalker, I guess there is the old code running and the one that you've recompiled and reinjected. Is it like just a big jump from one to the other that you just patch, or is it?
So the way it works with Stalker, Stalker is very different from Interceptor, which I showed in the beginning. But so Interceptor modifies it and just writes a jump in the beginning of the function, and then it has already relocated the first instructions that it overwrote. And it also has some tricks where it can jump through a nearby elf or Mac-O header if there's not enough space for a jump. And so that has some tricks, but Stalker is different. So if you stalk another thread that you're not in, and then it's just going to suspend that thread, read registers, take the program counter register or IP or whatever, and generate code for what's there up until the first branch, like I showed you. And then it's going to replace the PC with the instrumented version, and it's going to resume that thread. And then when it gets to the end of the basic block, it's going to call into Stalker to generate more code and so on. And the tricks that I talked about will make it faster, so it will be able to go directly between blocks at some point if you configure it like that. However, if you're tracing the current thread, that's when it will actually just look at the return address of the function and generate code for that, replace the return address and return. So that way you can combine it with inline hooking, so you could hook some interesting API and then start stalking synchronously itself until it leaves, for example, and then you could stop stalking there.
Okay, very interesting. And I have another question. Just if you like, what dependencies does your agent have? Like, is it something that relies on I don't know, some libraries, or I'm just thinking how hard would it be to inject this in a running kernel, for example?
It will need some work. It tries to avoid libc dependencies as much as possible. It has some libc dependencies, of course, but the long-term goal is to reduce that more and more. So for now we have TLS emulation, so we emulate thread local storage, for example, so we don't have to call the OS APIs to do that on some platforms to avoid like re-entrancy issues if you hook the TLS APIs, for example. So it's a work in progress, very much.
And the code loader, is it your own, or is it DL open and you're just relying on the?
You mean the injector, or?
Yeah, injector. So
yeah,
I don't have the vocabulary.
Yeah, it's my own. But it has different implementations per OS. Mac OS and iOS is the most advanced because in that case we don't actually touch the file system. We just map directly into the target process. So the target process can be sandboxed. It doesn't need to have file system access. We can just map directly in. So even DLD, the dynamic linker, doesn't know about us, about the library. All right, thank you.